As the last part of this lecture, let's discuss a very interesting topic. That is to say, if we know the initial value and the change form of the whole circuit, how can we semi-qualitatively draw the waveform of any branch variable? We give a few examples. For such a RLC series second-order circuit, as we discussed in lecture 55, it is overdamping when the resistance is 5 ohms. The two characteristic roots are -25 and -100. Additionally, because the whole circuit is a zero-input circuit, so any branch variable is with a form of a times e to the power of minus 25t plus b times e to the power of minus 100t. So if you want to draw the waveform, we need to do three things. The first is the initial value, the second is the derivation of the initial value, a third is the steady state value. Now we give two examples. For the capacitor voltage, it is easy to know that UC0 plus equals 3 volts. DUC over dt t equals to 0 plus equals minus 1 over C times IL0 plus in the circuit. We know that IL0 minus equals 0, so it is equals to 0. Because it is a zero input circuit, so the steady state value of UC should be 0. So we know that UC changes from 3 volts with a derivation of 0 and eventually attenuates to 0. Its semi-qualitative waveform should be like this, starting from 3, decays to 0. If we are interested in IL, we know that IL0 plus is 0. For DIL dt, t equals 0 plus, we have to solve UL. We need to use KVL here. So it is 1 over L times UC0 plus minus RIL0 plus. Because IL0 plus equals 0, so it is equal to 1 over L times UC0 plus, which is greater than 0. Similarly, we also know that the steady state value of IL is 0. So for IL, it starts from 0, increases at first, and then decreases, eventually attenuates to 0. Its semi-qualitative waveform should be like this. You might as well use multisim to verify it, the semi-qualitative waveform. It should be noted that the case we gave is overdamping. As we know from lecture 55, waveforms of overdamping and critical damping are very similar, so we won't cover those again. For the case of underdamping with a resistance is equal to 1 ohm, it's easy to get its two conjugate complex roots are in such a form. Based on the same initial value, we also know that UC0 plus equals 3 and DUC over dt t equals 0 plus equals 0. The steady state value of UC is equal to 0. How can we further use these two characteristic roots? We might as well write out the general solution of UC like this. Here K and theta are underdetermined coefficients. In the first order circuit, UC must be equal to UC steady state plus UC0 plus minus UC steady state times e to the power of minus t over tau. We said a very important view there that UC tends to be 0 after 3 tau to 5 tau. Do you find for a transient process of second order on the damping circuit is also a process of attenuation. So here 12.5 is very similar to 1 over tau in the first order circuit. Thus, we can know that the transient process of the whole circuit is 3 times 1 over 12.5 to 5 times 1 over 12.5. During the period of 0.24 seconds to 0.4 seconds, it will be over. What does that mean? Please look at the attenuating oscillating frequency, which is 48.4. It is actually equal to 2 pi over capital T, we can get the attenuating oscillation period of the sine wave with 48.4. That is to say, the period is equal to 2 pi over 48.4 equals 0.13 seconds. Combining these 2 points, we can know that the whole damping oscillation waveform is over during 2 or 3 periods. So we know that UC starts attenuating oscillation from 3. The derivation is 0 at first and eventually decays to 0. The whole process of the attenuation needs 2 to 3 periods to complete. So its semi-qualitative waveform is like this. You might as well use multisim to verify it. In the end, let's take a look at the no damping. For the case of no damping, we can solve its free oscillating angular frequency. So we can also get its period. And we also know that any branch variable is a sine wave without attenuation. Now the question is that if we want to draw the waveform of IL, what's the maximum value of the sine wave? Because the circuit is a no damping, so any time the system energy is the same. We know that only the capacitor stored electric field energy at first, which is 1 over 2 times 0.01 times 3 square. And we have introduced in lecture 55 that the inductor current is the maximum value when the capacitor voltage is 0 and vice versa. So we know the energy when the inductor current is the maximum value is the same as the energy at first. So we get 1 over 2 times 0.04 times IL max square. So we can get IL max equals 1.5 ampere. With the maximum value and the period, and in our previous discussion, we have already known that the inductor current starts from the 0 and the derivation at the start is positive. We can easily draw its semi-qualitative waveform like this. You may also use multisim to verify it. In this lecture, we have discussed a variety of intuitive methods. It's very important that by using the state equation and the output equation, we have the systematic method for solving any branch variable response of the second order circuit. After finding the expression of the branch variable, we also introduce a method to draw the semi-qualitative waveform of any branch variable. These methods are very useful and have wide range of applications in engineering practices. I hope you learn carefully and master them. This is the end of this lecture.